Hello again. This is another installment in the my attempt to work as many problems as possible as practical as I can get done. And I've started on chapter 8, and I'm going to get in a little on chapter 9 eventually. But I want to cover all the gas laws, or at least the kind of thinking that you use in working with the gas laws. And what you see in front of you is sort of a kind of a depiction of a lot of problems that, not a lot, but several problems that show up in the course of chapter 8. And some of them are, piston cylinders and pistons like these, or in some other cases, balloons of different sizes. But they're all basically the same idea. Give you a pictorial representation of something that you are expected to deal with mathematically. And I think it's a good idea to do something like this so you can sort of visualize what you're actually working with. Okay, well, this is section. What section? This is 8.2. This is Boyle's Law. And so, as I said, I'm just going to work problems here. This is 8.11. Okay. It says, and I'm reading from your text, this is page 267, that the air in a cylinder with a piston has a volume of 220 milliliters and a pressure of 650 millimeters Hg. Okay, you see, I wrote this down. I kind of cheated. I actually started working on this earlier. There's a section A and B in this. So there's two things here. So A is to obtain a higher pressure inside the cylinder when the temperature and the amount of gas do not change. Would the cylinder change as shown in A or B? Well, geez, that's I've got four things here, and well, we can cut out one of them. Actually, we can leave them all here. Let's do it like this. I got my whiteboard. I never get the thing oriented right. Okay. Okay, this is the initial condition here. And we'll scratch this one because it's the same as the other one. So we can call this one A and this one B. All right, so they're asking which cylinder is going to be the one that shows this. There's no change in temperature or N. Okay, so that's nothing's happening there, but there's an increase in pressure. Remember now when we talk about increase in pressure, Boyle's law, P1 V1 is equal to P2 V2. Boyle's law. When you're working with pressure and volume and no other variables, you're talking about Boyle's law. So just think about it. P1 V1, that's your initial, that's your 220. I'm sorry, oh, that's not right. 220 milliliters. This is 220 milliliters. And this is 650 millimeters Hg. So we've got that down there. It's going to be the same no matter what happens. And they're telling you that there's an increase in pressure. So you're asking which of these two cylinders, A and B. So for now, we're not paying attention to this one, okay? So which one is it? Increase in P. So pressure 2, P2, this one here, is greater than P1. Okay, so P2 is bigger than P1. It's more than 650 millimeters. If that's the case, what has to happen with the volume? Pressure gets higher, volume has to change so that the product of pressure and volume are the same as that in on the left side of the equation, P1, V1. You should be thinking, well, if pressure goes up, then volume must go down, which would be the case. So if the volume goes down, pressure goes up, volume goes down, you're squeezing this stuff, okay? You're putting more pressure on it, you're squeezing it. Okay, so it's got to be A. It's got to be this one. That's going to be your answer. So, you know, that's the way you work this, okay? Now, that's part A. Part B, and I guess I'm gonna have to move this a little bit to get the thing to make more white space here. If the pressure inside the cylinder increases to 1.2 atmosphere, P2, in other words, P2, P1, you got P1, 650 millimeters Hg. P2 is going to be 1.2 atmospheres. What is the final volume, V2, in milliliters of the cylinder? You see where I got that? Those are your givens. Okay, P2, 1.2 atmospheres. P2 is 1.2 atmospheres, but V2 is what you want, and they want it in milliliters. Okay, so what we have here, we've got V1, volume 1 in milliliters, so we're good there. We've got pressure 1 in millimeters Hg and pressure 2 in atmospheres. We're asking for the volume in milliliters, so we're really not worried about the pressures, except that we have to have them in the same units. All right, so let me move this a little bit. Move this up some. Let me copy. I better copy this down here before we do this. P1 V1 is equal to 650 millimeters, and don't worry, we'll worry about, it's going to be times 220 milliliters. All right, so those are the units we have there, and then P2 is 1.2 atmospheres. So we're okay with milliliters. We've got volume 1 in milliliters. We need volume 2 in milliliters, so we can just stick with milliliters there. But, oops, don't want to do that. So what do we do with pressure 2? Well, there's two things we could either convert this, we could convert P2. We need the pressures in, we need both pressures in the same unit. So we can have P2, we can convert that to millimeters Hg, and remember the conversion factor, it is 760 millimeters Hg. Oop, that was wrong. Per 1 atmosphere. So 1.2 atmospheres, that's going to give us, you multiply that, you see atmospheres are going to cancel, and you get 1.2 times 760. Waiting for I have a solar powered calculator with, I think the battery's gone, so it takes a while for this thing to come up. Here we go. Okay, 1.2 times 760. I get 912 millimeters. All right, now you notice here we've got 1.2 atmospheres, which is two significant figures. We have 650 millimeters Hg, It's hard to tell whether that's 2 or 3, but we have 1.2 atmospheres, so we have 2 significant figures there. So we really don't need to worry about too many of the others. Everything else is 2 or 3 digits. So let's go through these calculations, and then we'll round at the very end. Even if no matter how we decide to handle the units with P1. Let's just convert that to atmospheres. 650 millimeters mercury times 1 atmosphere per 760 millimeters. Now you should all be able to do this, but it doesn't hurt to do this once in a while. Okay, I get 0.855. Let's round it to 0.86. Okay, it's 0.86 atmospheres. One or the other. Either way, we're going to have 2 significant figures. So we can do that. 912. We could round that to 910, but it looks like atmospheres is a little easier to work with. We're going to work the other one too, but let's do this here. We're looking for the volume in milliliters, so we're looking for V2. We're given P1, V1, and P2. We want V2. We want it in milliliters. All right, we're okay with pressures now because we've got our pressures in both units. We got both pressures in both units, so we can take our pick. So we want V2. Put this over here. Milliliters. And we're starting with P1 V1 is equal to P2 V2. P1 V1, I said we're going to use atmospheres, so let's use atmospheres. P1 is going to be 0.86 atmospheres times, where are we here? 1.2 times, wait, P1 V1, where's V1? V1, 220 milliliters, right? 220 milliliters, yeah, times 220 milliliters. And that's equal to, I jumped the gun here. You know that's what we're looking for. So I can erase that now. And that's equal to pressure 2, which we have established as 1.2 atmosphere. And we haven't established it, it's been given to us, times V2. Okay, so now we have to figure this out. Well, we're solving for V2, so let's, if we do that, all we really need to do is divide both sides by P2. So P1 V1 over P2 is going to equal V2. So 0.86 atmospheres times 220 milliliters divided by 1.2 atmospheres. And remember, your pressure's going up, so the volume has to go down. So we're worried about where's the volume going. Okay, so 0.86 divided by 220, no, 0.86 times 220 divided by 1.2. I get 158 milliliters here. That's actually rounded from 157.66666 and so forth. We're going to have to round that anyway. So, but that's our V2. And we say here we've got 2 significant figures here. Got 2 significant figures here. And this 220 is that, we don't know that 0 is significant anyway, but we have 2 significant figures. So we have to round this to 160 milliliters. And that's the way you're going to do the problem. You see what we did? We put down what we knew. We put down what we needed to get to. And this isn't exactly the nice formal, neat way they did it. This is the way you work problems on a quiz, on an exam, stuff like that. You really have to get it. You have to get this stuff down and put it down in the right order, put it down in the right places really quick. So we do that, and we get 160 milliliters. Okay, so let's look at the end of the chapter, the back of the chapter, and see what they give us. What is an 8? Well, I skipped over all the way to chapter 9. 811, I think it was. 811. The pressure is greater in cylinder A. Okay, and they give 160 milliliters there. So we got the answer that the book got. So you have at least some corroboration there that I think we did this right. All right, I'm sure you believe it too. But you want to work a lot of problems where you're given the answer so that you don't end up, you develop good habits. I mean, you learn how to set these things up to do it right. And then when you don't have the answer, you got a better chance of getting the answer correctly. Of course, when you're doing research, original research, there is no answer to look up at all. You have to figure it out, and you have to convince everybody else that that's the case. So, okay, we got that one. Let's do another one. We're going to do the next one, 812. It looks like I got to start a new page here, so I will. We're going to do 812. Now this one uses balloons. This is also on page 267. This one uses balloons, but that's okay. We have a graphic here that will serve the purpose. And just bear with me a moment here, and I'll bring that up. Okay, here's the diagram. Now, 812 gives you balloons, but it doesn't really matter. It's different volumes. Okay, a balloon is filled with, it reads, a balloon is filled with helium gas. So it gives you a balloon. Balloon, helium gas. Which of the following changes are made with no change in temperature? When each of the following changes are made with no change in temperature, which of these diagrams, A, B, or C, shows the final volume of the balloon? All right, well, this is initial. This is A, this is B, this is C. And if you look at page 267, 812, you'll see that I did this pretty much the way they did. It's just I'm using cylinders and pistons. They're using balloons. It's essentially the same situation. Okay, so we have three situations. We have one, the balloon floats to a higher altitude when the outside pressure is lower. Okay, balloon. Am I spelling this right? Yeah, I spelled it right. Higher altitude when the outside pressure is lower. B, the balloon is taken inside the house, but the atmospheric pressure does not change. They're expecting you to think on this one. C, balloon goes into a hyperbaric chamber. pressure increases, all right, goes up. Sometimes you'll say, people say INC, it doesn't mean incorporated. In situations like this, it means increases. All right, so we need to decide which of these situations is, which of these situations correlates with each of the A, B, and C. Okay, the balloon is higher. It, what do we say? The balloon floats to a higher altitude where the outside pressure is lower. The balloon is taken inside, there's no change in the pressure. And the balloon is taken to the hyperbaric chamber. And they mentioned no change in temperature. Okay, so this is Boyle's law. Yeah, this is classic Boyle's law. P1 V1 equals P2 V2. Okay, so which of these, A, B, or C, correlates with A, B, and the capital A, capital B, and capital C correlates with A, B, and C? The balloon is higher when outside pressure is lower. Outside pressure is lower. Well, that's going to tell you, to me, the wording on this is a little bit tricky. So the balloon is higher when the outside pressure is lower. Well, if the outside pressure is lower, that means that the balloon is going to expand. If that means pressure is lower, so the volume is higher. So that looks like C. Okay. So we're guessing that is going to be C. B, the balloon is taken inside, there's no change in pressure. Well, they say there's no change in temperature, and if there's no change in temperature, then that's not going to affect it. There's no Charles Law things going on. And if there's no change in pressure, then we're going to have the same pressure. We're going to have the same volume. Okay, P1 V1 is equal to P2 V2. Well, if P1 is equal to if P1 is equal to P2, then V1 is going to be equal to P2. It's going to have to be. So we're saying that's going to be B. And if the balloon's taken to a hyperbaric chamber, that means the pressure is increasing. So P1 V1 is equal to P2 V2. Let's write this down. Okay, if P1 goes down, volume has to go up. All right, that's a necessity. If P1 stays the same, P1 stays the same, then P1 is essentially P1 is equal to P2. And that's what they're saying here. It's one of these things. You have to learn to read these things too. If there's no change in pressure, that means P1 is equal to P2. Initial and final situations are the same. So you have that's one of these little things you want to look for. So that's going to be B. A balloon is taken into a hyperbaric chamber where the pressure increases. Okay, pressure increases, volume has to decrease. Okay, so where are we here? See, let's see, we got AC. Where does the volume decrease? Well, the volume decreases in A. All right, so the answers you're going to give are going to be, let's see, the balloon higher, the balloon floats to a higher altitude. I wrote this down in a confusing way, I realize that. Okay, moves to higher altitude. So that's going to be C. So this is going to be small c. The balloon is taken inside, there's no change in pressure. If there's no change in pressure, there's no change in volume. So this is going to be B, small letter B. Balloon is taken to a hyperbaric chamber where you're putting a higher pressure on it, so it's going to shrink. So this is going to be So this is going to be C. All right. So I think one thing, your book uses balloons, and I didn't try drawing balloons because cylinders and pistons are easier to draw with Microsoft Paint. Actually, it probably takes a lot more time to draw them this way, but still, it works the same way. It doesn't really matter what the volume is, if it's a balloon or a cylinder with a piston. Volume is volume, and pressure is pressure. So you're going to get the same effects either way. So I did this. I put this in the same order that they did, and again, that's the way you work this type of problem. Now, I'm going to move on to the end of the chapter. I plan to do more of these, but just in case I don't, I'm going to have some, I'm going to do some stuff here. I'm going to do one, which I'm going to have to look for it, but I'm going to have to stop the recording for a second and find this thing. Okay, here we are back. This is problem 866. And this is an interesting problem. If you look in your text, you will see little circles with little balls in them, which are molecules. And there's 6, if you count them, there's 6 in each one. So we've got the same stuff in all of them. So let's go ahead and put these dots in here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, okay. We didn't really need to put them in. The main thing is the volume here. They give you an initial condition, and they give you 1, 2, and 3 outcomes. There's 3 of them. And we're given 4 changes of conditions, and we're supposed to assign each one to one of these 3 cylinders. Or in the case of your, what do they call it? Flexible container in the text. But it's the same problem either way. So let's work on that. Let's look at the changes that happens. Temperature increases. So T1 increases. So to T2. And if you think about what that means T2 is greater than T1. It's good that these qualitative things, you need to think about them. And pressure does not change. So P1 is equal to P2. This is, you'll see where I'm getting at working problems like this, because there's, I think, simplifications in notation that can help you. Okay, so that's the first thing that happens. B, temperature decreases, so T1 decreases, so T2 is less than T1. These are absolute temperatures, Kelvin temperatures. Okay, so they're all positive, so they go from 0 on up, or from whatever they are on down, whichever the case may be. Pressure does not change. P1 is equal to P2. C, atmospheric pressure decreases if temperature does not change. Okay, so now temperature doesn't change, so T1 is equal to T2. And I guess we have the atmospheric pressure decreases if pressure. I guess this is atmospheric pressure. Okay, so the pressure decreases, so P2 has got to be less than P1. Remember, you have a pressure and the pressure decreases, so the decreased pressure is P2. And we go to D, doubling the atmospheric pressure and doubling the Kelvin temperature. Okay, so now P2 is 2P1, Okay, we start with a pressure, we double it. Our new pressure is twice P1. We double the Kelvin temperature. So T2 is equal to 2 T1. Okay? I hope you can see that. Okay, so what are we looking at here? Well, we're varying pressure and temperature, so that sounds like Gay-Lussac's law. But on the other hand, we look down here, and we're changing the volume. So what we're really looking at is the combined gas law, isn't it? P1 V1 over T1 is equal to P2 V2 over T2, right? That's what we're looking at, combined gas law. We have temperature here, we have pressure here, and we have volume here. All right, so we know how they operate. We know how they interact. But they interact according to this baby here. All right. Okay, so let's start plugging numbers. Okay, we know. Okay, first of all, we know that P1 V1 over T1, that product and quotient must be equal to P2 V2 over T2 because we have the same amount of stuff in the cylinder. It doesn't the amount of gas doesn't change. So that's staying the same. So what we do is we plug in these relationships that we figured out here and see what happens. Okay, so P1, let's do A. Let's do A first. We have, okay, P1 V1 over T1 is going to stay the same all the way through. So what do we have? T2 is greater than T1. Okay, T2 is greater than T1. We'll do something with that. But let's P1 is equal to P2. So P2 is equal to P1. So we can just leave P1 in here. And we're going to get a V2. We don't know what V2 is going to be. And T2 is down here. T2 is greater than T1. All we need to know is it's greater than T1. Okay. And you notice we can cancel. The P1s actually cancel here, if you think about it. So actually, we're looking at V1 and just the volumes here. V2, we don't know what V2 is. We're trying to figure it out. Well, T2 is greater than T1. And if we can, they don't say how much greater. They just say it's greater. So we can say, oh, what's going to happen? It's more than 1 times T2. Okay, so let's just throw a number in. Let's say 2 times T1. All right. Okay, well, what's going to happen to the volume? Okay, you're dividing by T1, or by T2 actually. So this number is bigger than this number, which means it's going to, if we don't change V2, this number, if V1 stays the same, then this thing is going to get smaller. So V2 is going to have to get bigger, right? So V2 must increase in order for this relationship to hold. You think about what the numbers are doing. So V2 has to be bigger. So this is going to be A here. We've got that one. Okay, B, let's do another one. I think this could be a little confusing. So this is one you might want to think about a little bit. Think about what I'm doing. Okay, we have, again, with B, we have P1 V1 over T1. And that's equal to, now we have, okay, T2 is less than T1. So let's say let's say half, all right? And I think you already see what we're going at here. And where we're going here is we're going in the opposite direction as we did with item A. So we see that P1 is equal to P2 here. So this is P1, but now this V2, okay, what's going to happen? This 0.5, okay, this is smaller now. This 0.5 T, this T1, it's less than, we can just throw in an arbitrary number that's to make it less than the original T1 is what I'm saying, because we say it's less. They don't say how much is less, and it doesn't really matter how much less it is. You're going to get the same. You're going to get the same conclusion either way. So if so, what's going to have to happen is V2 is going to have to decrease as well. And let's come back here. If we just arbitrarily said 2T1, what has to happen, if you think about it, is 2T1 in order for this value to be the same as this one. Whatever's down here is going to have to cancel up here, so it's going to be 2V. Going to be 2V1. Okay, this is essentially what we're doing. So they're going to cancel. All right. So the same thing's going to happen here. If you have a lower number for T, if you have this temperature decreases here, this volume has to decrease as well in order to compensate for the effect of the temperature. So this is going to be, the volume is going to have to decrease. So this is going to be B. This one here. That's what I'm saying. Okay, C, where you have T2 is equal to T1 is equal to T2. So let's P1 V1 over T1 is equal to P2 is less than P1. So P2 is, let's say half P1. I don't know, it's less than P1. We just need a number less than P1. And we just say, all we're looking to do is see what's going to happen to the volume. Is it going to go up or down? That's really all we're looking for. Or is it going to, maybe it won't change. Okay, so P1, and now we need to know what let's put V2 in here. And T1 is equal to T2. Remember, we're working on C now, so that we can say T1. So what do we have? We have reduced this product here. We've reduced P1 V2 to half of its prior size. So we need, remember, P1 V1 over T1 is staying the same, you notice, which means this value, P1 V1 over T1, is staying the same all the way through. Okay, so we're comparing everything to that. So, okay, we have 0.5 P1, that's P2, okay? Okay, we're saying, in this case, we're saying, T2, we're saying T2 is equal to 2T1. We don't know that it's 2T1, okay? It could be anything, but it's more than T1. And the same thing with the where was it, the what am I saying here, the half, this one and this one, the half T1, T2 is equal to half of T1. And we're doing the same thing here. Okay, so what we need for the volume is going to have to change in order to keep this product, 0.5 P1 times V2 divided by T1, equal to P1 V1 over T1. Okay, so, well, what are you going to have to do here? Well, you're going to have to, V2 is going to have to change in order to compensate for this lower number. So it'll be 2. And so if 2 times 0.5 is 1, so now everything's the same. So the volume is increasing. Okay, think about that. That really, this looks a lot more complicated than it is. There's a lot of numbers to keep track of, but this is one way, one way of looking at it. This, okay, here you have P2, P2, which is less than P1, and the temperature stays the same, so pressure drops. So volume has to go up in order to compensate for it. So this is also going to be C. Notice we didn't really say for sure. We don't know that it's doubled for sure, but it's more. D, it's an interesting one. Let me go back to here, D. P1 V1 over T1 is equal to, what are we doing here? We're doubling temperature, we're doubling pressure. So 2P1 times V2 over 2T1. Remember, temperature's doubled, so T2 is equal to 2T1. And what happens to the volume? Okay, well, 2's cancel. So you got P1 V1 over T1, P1 T1 over V2. Well, these are equal. V2 has to be the same as V1. So there's no change. Okay, that's how you work that. That's those are a couple problems that could be a little challenging. There's, if you want to call it a trick, I don't know if you want to call it a trick, but this is something that this is some of the reasoning you use. Sometimes it's kind of semi-quantitative. It's really not quantitative, but you're looking at which direction changes, which direction is the change going? Is it getting bigger? Is it getting smaller? Is one getting bigger and one's getting smaller? Or are they both getting bigger and both getting smaller? There's a number of things that you could do with this. And you could take this problem and you could mess with all three variables. Okay. Well, you need to, you could set this problem up. I shouldn't say it that way. You really wouldn't want to change. You'd only want to change two variables, but you could take any two variables you wanted to change. And in this case, they didn't really do anything with volume. We could have adjusted volume as well. But these are relationships that hold between pressures, temperatures, and volumes and numbers of moles in all of these things. And that, I think, is one of the important concepts to grasp. This is all predictable. This stuff is all, it works according to a scheme which is, which has been discovered over a couple of centuries, but this stuff is all rational. It all fits into a pattern or several patterns. And if you sit down and you just work problems, you'll get it. So this is another, I'm going to be doing this, the rest of the semester. I don't know how much of this I'm going to be able to do because, there's other things, lectures and grading, and we've got a lot of things to do with setting up exams and that essay and so forth. But I hope this is helpful. I hope you get something from it. I hope you look at it. And as I said, I've said it many times. I'm going to keep saying it. You got to work a lot of problems. Work problems before you do the homework. Even before you do the homework, work a bunch of problems. Just scatter, a couple problems from each section. See, get the feel of what's going on before you start trying to do that. And then after you do the homework, even work more problems before you do the quiz. I know that sounds like a lot of work, and it is a lot of work, but that's how all of us got through. Those of us who are teaching it, that's how we got through it. So there's really no royal road to Rome, as it says, as they say. That's the way it gets done. So it's for me, it's getting close to 10 o'clock. I don't know when you're going to be looking at this, but I'm going to sign off here. I'm going to get this thing onto YouTube, and I'm going to get the link to you. I got another one that I did earlier, and you can take a look at them. And like I said, I hope you find them useful.